All right, we're recording. So no sounds? Try this. What's back? Equals. First, you're going to have a little practice graphing that. And I'm going to go from the interval from -2 to 4 using all 5 Riemann sums. Yeah.
I forgot. How many of the Riemann sums did Riemann actually make up?
He made 4.
4 of them?
Yeah, the fifth one, Simpson's row, was made by a mathematician whose last name was Simpson. But it was lumped into the Riemann sums just because Riemann invented it and it's the category. So basically any slice-based method of approximating the area under a curve is called a Riemann sum. And Simpson's row just happens to be a really, really good way of doing that. And he based his work off of Riemann's work. So I'll have to look it up and see if it will. I'm going to look that up and see if Simpson actually did that voluntarily or not, or whether people just started calling it real Riemann sum. First things first. What's step 1? Yeah.
I have another.
Yeah, if it's fast.
Well, yeah, but like, I'm just kind of curious, like, you know, who would like, no, like, I'm not trying to like disrespect calculus or anything, but who would like want to do that? Like, you know, just sit there and be like, oh, I'm gonna find the area under the curve. Like, what's kind of the point, I guess?
Well, sometimes you have to find areas of irregular shapes. This happens all the time in, I mean, maybe not necessarily in a lab, but trying to think of it. Because I'm not an engineer, so I don't know it off the top of my head. If you're trying to find, like say, for example, has anybody heard of the Tacoma, I think it's the Tacoma Bridge. It used to be called Galloping Gertie. It was a spanning bridge across a place in Tacoma, Washington. I think it was Washington. Something about it, people didn't understand physics as well as they do today, but they had a bridge spanning this chasm, this canyon, and something started happening where the wind, it wasn't just pushing the bridge, because the bridge was built pretty well, solidly. Vibration started hitting in the bridge itself, and it was a big bridge. It was made out of concrete and steel and things like that, and it started wobbling back and forth. It's called oscillating. Oscillating is like it kind of goes like this, and here's the bridge, and people are driving over it. Now, their car is going over it as they speak, and it started doing this. It literally started bending and wobbling, and they nicknamed it Galloping Gertie, and people would just drive over it while it was kind of unnerving, where your lane would all of a sudden go up by like 1.5 feet, and then go down by 1.5 feet, and then go back up, while the other side was bucking. Slowly, but people would, eventually it started getting so bad that they closed the bridge, and the bridge eventually tore itself apart and collapsed on a particularly windy day. And they could not figure out why did it happen. The best guess is, ever take out like a soda bottle top, like those glass, not cans, and blow over the top of it, and it goes, it makes this kind of a note. That resonance is what they figured shattered the bridge. If you just keep blowing and blowing and blowing over the can, it starts getting louder, louder, louder. And if it's just perfect, it resonates. Boy, this is going to sound funny, but if in certain tile-laden bathrooms where there's not much carpeting or things like that. There are certain parts in the room, and there are certain parts, this is gonna sound totally fun. I'm recording this too, so I'm doomed anyway, so might as well. It's gonna be recorded on YouTube forever. But there are certain porcelain items and things that are fragile that have what's called a vibrating frequency. Almost everything does. Trying to think of a good example. The only one I can think of is a really stupid one, and it sounds off color. But toilets have vibrating frequencies. If you hum a certain note, it resonates and sounds twice as loud. Now, you don't actually stick your head into the toilet. I was told this by a friend of mine who was actually, he was sick. I won't tell you why he was sick, but he was throwing up, and he was in the, and then, all right, he had a little too much to drink, but I did not, by the way. This is long before I met him. And he was just sitting there getting over being sick, and since he was not in all of his faculties, he started humming to himself, and then found out that one of the frequencies was really, really loud. And he said, "Whoa, I just found the vibrating frequency of the toilet." This is your life's work. Good luck with life, my friend. But everything has a vibrating frequency. For example, glass. You ever seen, they have videos of it, where if you have an opera singer who sings a really high note, loud enough and amplified enough, it'll shatter the glass. It will not shatter every glass. And it doesn't even necessarily matter how thin or thick it is. Well, if it's super thick, it probably won't shatter. But there's a particular vibrating frequency. Like if the glass is empty and you ding it, somebody who's good at music or has a good ear can figure out what note that is. And if you fill it up with a little bit of water and ding it, it changes the note. The exact same friend of mine, ironically enough, who had the porcelain throne episode, was over at a restaurant, and he was driving the waitress nuts because he had like 5 or 6 wine glasses, and he had like little bits, different things of water, and he was going ding, 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 ding. And you can play things on it. I know this is getting off topic, but one last thing, which is super duper cool. It's based on this. This is a really super long answer to a short question. But have you ever seen it where if you wet your fingers and you run your finger circular around the top of a well-made wine glass, crystal glasses, it'll start to sing. That means it's the vibrating starts, it gets just, you can vibrate it just right, and it's kind of like playing a violin. The vibration will cause a note, and it depends on the vibrating frequency of the glass. So if you find the vibrating frequency of the glass and sing or play a note or something really loud, it'll tear itself apart, it'll shatter. So if you have a plane of glass, not safety glass, but regular glass, it has a vibrating frequency. If you can find it, people use it, put a stethoscope to it and then ding, ding, ding it, and you can find the note, and then you take a speaker and you blast that note at it, it'll shatter. That's kind of sort of what happened to the Tacoma Bridge. The wind happens to hit the right vibrating frequency, and it kept getting worse and worse and worse, and then it tore itself to pieces. So why would you ever need to know the area under the curve? The area on the side of the bridge had a big difference in what the vibrating frequency was. And if you put holes in strategic places along the side of the bridge, now just letting the wind go through is one thing. It helps keep it from, just being pushed. But that can also be bad, because if you put a certain number of holes, you change the vibrating frequency, and you might make it worse. So you need to know the area on the side of the bridge in order to avoid that. Like, the more you know about this, the more you're gonna, who knew this was gonna happen? But it was millions of dollars poured in. This is in the 1920s. There was a lot of money, and the thing shattered. I think they rebuilt it. I'm not sure. But
Videos of the bridge.
there is a video. Have you ever seen the video on the bridge? It's, look up Tacoma, Tacoma, Tacoma Bridge. What's that? He didn't, but his dog did. Yeah, there was a scientist who was taking measurements on the bridge while it was particularly bad, and it started breaking apart. He ran. His dog was in his truck, which was in the center of the bridge. He ran, and then he thought, "Oh no, my dog didn't come with me." He tried to get back to save his dog, but the bridge collapsed, and the dog and truck both went into the canyon and died. Well, the truck didn't die, but the dog did. The truck just got smashed.
Did the guy die?
No, he was safe, but that was sad. Anyway, that was an indirect, very long answer to your short question. But this does come in handy in the weirdest places. So that's why scientists have to be prepared. And the more people who are trained in this, the more people who would be called upon and say, "Hey, our bridge just shattered. Can somebody explain this?" And then they say, "Oh, let me get the area under the curve. See what happens." So, step one. What do you do? How do you run a problem like this? Riemann Sums. What's the first thing to do? Because you're going to be doing this on a test. Go. Upper sum. How? How do you start? What does an upper sum mean, by the way? Go, Pete.
Oh, I was just, well, that's like where you take the top, like a portion of the graph and like make a little rectangle or something.
Okay, so you slice it into rectangles, but as you're following the curve, let's just say you make like here's where you're going to make your slice. How do you tell which one to use as the height? How about for an upper sum? The tallest one, the upper one. And for a lower sum, you use the lower one. If they're both tied, then you just, who cares? You just pick one. Is everybody clear so far? But in order to know which one is higher, what do you have to do first? Anyway, Jeff.
Look at it.
Yeah, but I have nothing to look at yet.
Oh, graph it.
Yes, graph it. Write that down in your notes. Step one in Riemann sum, graph the function. You won't have any idea what the heights are if you don't see what the function is. Somebody talk me through it. How do you graph this thing? Anybody spot any objects or any points or any anythings? Talk me through it. Max, help me out.
So you could look for
There's an object that's a little more obvious first. We can find roots if you want.
degree 1.
What's that?
Is it degree 1?
It's not degree 1 actually. It looks like it is, but the x is in the bottom, so it's really degree what? What's the 1 over x is really x to the what power? Oh, math people. It's actually from first year algebra, believe it or not. No, help me out. 1 over x is x to the what?
-1.
X to the -1. This is degree of -1, or 0 depending on point of view. But it's not a polynomial. So it does not, it's not a line. So how do you graph it? Can you spot any objects whatsoever? John, help me out here. Are there any objects you can spot just by looking at the equation? Correct. There's a vertical asymptote at x equals 2. Draw that in. I know ahead of time that I need to go from -2, x equals -2, to x equals +4. So that's how far I'm going to go. Can somebody spot anything else for me? How would you graph this thing if it doesn't seem very helpful? People who remember your pre-calc, how do you find a horizontal asymptote?
Send x to infinity.
Send x to infinity and watch what happens. Do it. If I want to find a horizontal asymptote, you take x and send it to infinity or -infinity, whichever you like. Should work both ways. Try sending x to infinity here. What happens to it? As x goes to infinity, 1 over x minus 2 plus 1 goes to what? This is actually a limit problem. Pretend x is getting really, really big. Yeah.
Well, it's getting closer and closer to zero.
Yeah, the fraction is getting closer and closer to 0. And then how about this? What's the answer getting closer and closer to? 1. Yeah. Does it make sense? This is getting closer and closer to 0. It's 1 over a billion minus 2, 1 over a trillion minus 2. It's getting microscopic. So it's getting closer and closer to 0 plus 1. So it's getting closer and closer. What does that mean? What did you just find?
Horizontal asymptote at 1.
Yeah, there was a horizontal asymptote at y equals 1. Okay. Good to know. How do you find any other points? At this point, no pun intended, there is no real sneaky way to do it. How do you graph anything that you've never seen before? Go.
Wait, is there a y-intercept at negative y equals negative?
Interesting. Y-intercept of what?
Or
There
it
is.
one or negative?
You tell me. How do you find a y-intercept?
Set x
Do
to 0.
it.
So it's 1.
Well, what do you get here when you plug in x equals 0?
Well, 0.
Try again.
0 plus, that's it. So it's, negative 1/2.
Negative a half plus 1.
Equals 1.
True.
It's the morning, but it's not that early. What's that?
Yeah, 1/2.
1/2. Good. So it has a y-intercept of positive 1/2. Right here. I'm going to mark that as 1/2 because anything that's not a whole number I mark. That should actually tell you something. I think, Max, you were talking about finding roots. There's a little bit of a problem. You can only find roots. I want everybody paying attention to this because you might have to do this. How do you find a root on something with two different terms? You have to make it into one big fraction. Let me write this down. You remember plus minus notation when you're doing this in pre-calc? To find roots, vertical asymptotes, holes and such, the whole thing has to be one big fraction. The roots are on top, vertical asymptotes are on the bottom. This will not work. A lot of people look at this and they say, oh, there's no x-intercepts. Not true. Watch. Suppose you have 1 over x minus 2 plus 1. Can anybody get a common denominator for me? Because they want to add these two things. How do you add a whole number and a fraction, first of all? Jeff. Yeah, put this over 1. What is the common denominator? Anybody know? Yeah. X minus 2. This has a 1, this already has a 1. But this needs an x minus 2, which is fine as long as you do it to both sides. Tell me what this should look like. It's 1 over x minus 2 plus what? Max, take over. What goes here?
X minus 2 over x minus 2.
Correct. Add them up. Now we have a common denominator.
1 plus x minus 2.
What is 1 plus x minus 2?
1x minus. Wait, why is this so hard?
I don't know. What's 1 plus 1x plus
1x.
negative 2?
1x plus 1.
Yeah,
Plus
yeah.
Negative 1.
So in other words, x minus 1. Make sense? Do you see it looks different than it was? Where's the root now? You can probably just see it. Michael,
1.
x equals 1. There's a root here. What I would like to do is mark a bunch of heights. Can somebody give me, now you notice we're going to be slicing this. What's the normal width of a slice? If you can get away with it. What's the easiest width for your rectangles? 1. Yeah. You can do 1/2 or 2 or something like that, but it makes your math a little harder. If you've got slices of a width of 1, the math is much easier. Let's do it. I want to find the height at x equals negative 1, x equals negative 2. I've already got this and this. There is no height here. And x equals 3, 4. give me the heights along the line, if you'd help me out. What's the height at x equals -2? Talk me through it. What's 1 over -2 minus 2? -1/4 plus 1?
Is it just positive 1/4?
It's 1 minus a fourth, basically.
Oh, so 3/4.
3/4. So the height here is 3/4. Mark it somehow. So the height of 3/4. Can somebody do the -1, Jack?
Yeah, -1 minus 2 is -3, so you have 1, -1/3.
Negative a
plus
third.
1, which would be 2/3.
2/3. Mark that somehow. That is a height of 2/3. Go to the other side. Jonna, what's the height at x equals 3?
3, or,
Plug it in here.
oh, sorry, 1/1.
Good. 1 over 1. Then plus 1.
Oh, plus
2. So there's a height of 2 here. Do one more. Try 4.
1/2 plus 1, so 1 plus 5.
1 plus 1, yeah, so 1.5. And mark that. That's 3/2. The graph is going to be doing this. Okay. Finding the area under the curve. I probably should have done a normal one first. Would you mind if I changed one little number first? I'll do this one next, but I want you to go from -2 to +1. I'll tell you why in about 5 minutes. Everybody got that change? Instead of -2 to 4, go from -2 to 1. We'll do -2 to 4 in a minute. But I want to do this one first because it's a little easier. Talk me through it. Let me see. Michael, help me out. How do you do an upper sum?
Look at the highest point for x.
I'm sorry?
The highest height.
Yeah. Now, how many slices are we going to be talking about here? Assuming that the width of each slice is 1, which doesn't have to be, but it's easier. How many slices does that make? Let's check. From -2 to -1, that's 1 slice.
Yeah.
From -1 to 0,
Oh, I missed zero, sorry.
so how many slices?
So 3.
3. Give me the height of the first slice.
3/4.
3/4. How do you get the area of a rectangle again? Pete, take over. Based on side. In this particular slice, use the upper height. What's the rectangle area? What times what? 1 times.
Oh, no.
The first slice is here. What's the upper sum height?
1 times, well, you have 2 sides of 2/3 and 3/4.
Yeah, which one did you use?
3/4.
3/4. Explain.
Well, because it's the taller.
It's the taller one. Upper sum uses the higher height. 1 times 3/4. Now that's the first slice. I have 3 slices. Max, take over. What's the second slice area?
Sorry, I was.
Yeah, okay. The area of the first slice, we're doing rectangular slices. So this slice area, this slice area, this slice area. I haven't drawn the rectangles because I don't want to make a mess. But upper sums use which end as the height? How do you, the top one. So in this one, we used a height of 3/4. What about the next one?
Would be 1/2.
Here's the slice.
Oh, 2/3.
2/3. So base times height. Are you still with me? Plus No, take over.
What happened?
Yeah, the third slice, it's either 1/2 or 0, so it's 1/2. Okay, math people? You're welcome to use your calculator or use your head. This is 3/4 plus 2/3 plus 1/2. Common denominator of 12 if you like. Tell me what you get. Leave it as a fraction. Have we got it? I heard it. Pete, what is it? 23/12. Correct. On the test, that's your upper sum answer. Lower sum. Jack, take over.
Well, you measure from the bottom,
Right.
it's 0,
Which slice do you do?
for the first one.
Yeah, we're starting over. So, what's the first height?
Oh, you do the lower point, so it would be, 2/3.
Right. So 1 times 2/3. You see why the 1 is there?
Yeah,
Yeah, that's the base. And then plus what? Keep going up.
1 times 1/2.
1 times
And
1/2.
then it's 1 times 0.
Then it's 1 times 0, correct. That should be a little easier to add up. It's a little annoying. What's the common denominator? This just gets eliminated.
6.
Yeah, go for it.
No, it's already, hold on.
And remember crisscross across. What's the answer? Okay. All right. 7/6. Yeah. Crisscross is that 4 plus 3 on top and then 6 on the bottom. 7/6. So the upper sum is 23/12, which is a little over 2, and then 7/6, which is a little over 1. What's the next sum? Matt?
Is the next one the midpoint?
That's
Or
the fourth one.
Trapezoid.
Trapezoid. How do you find trapezoid sum?
The upper sum plus the lower sum divided by 2.
Right, average those two. So upper sum plus lower sum divided by 2. At this point, you could do it in your head, but grab a calculator, it'll be faster. Let me grab mine. Where is it? Oh. So use parentheses when you're adding these, by the way. 23/12 plus 7/6 in parentheses divided by 2. What do you get? You can give me a fraction.
37/24.
And I hit the wrong button. Hang on a second. Over 6. 37/24. Correct. Fourth one. How do you do midpoint sum? John, take this one. What does midpoint sum mean?
You take the average of the height of each one, or the, sorry, not average, the midpoint.
Yeah, go halfway through and find the height there. Now, have your calculator handy. I would actually advise that you put this in the y equals screen. The 1/x minus 2. By the way, if it's in the y equals screen, you need parentheses here. Otherwise it will not work. You'll get the wrong answer. Go to the y equals screen, clear out any junk, and do 1 divided by parentheses x minus 2, parentheses, and then plus 1 at the end. The reason is now you can call up y1 and plug in anything you want. What's the very first value of x you can plug in? You can use a decimal if you want.
Or,
If it's the midpoint,
1.5, -1.5.
negative 1.5. So find the height at negative 1.5. So call up y1 and then parentheses negative 1.5. See what you get. And then convert to a fraction again.
5/7.
Yeah, this one's going to be 5/7. No, do the next one. What would you plug in for next?
Negative a half.
Correct. Negative 1/2. What do you get? Well, I'm trying to find the heights first of the individual middle points, the midpoints. We plugged in -1.5 into this thing, and now we're plugging in -0.5.
I just typed this in the wrong.
Okay.
I just deleted it, sorry, can you call someone else for the calculator?
No, it's okay. Does anybody else have it? It's a relatively nice fraction. If you want to do it manually, if you lost your y1, do 1 over parentheses -0.5 minus 2 close parentheses plus 1. Should give you the same thing. Grab your calculators if you don't have it. Try it.
Wait, what was the first one?
The first one was 5 over 7.
So you did y1, and then what did you multiply by?
Then you're multiplying by 1, basically. I haven't started doing that yet. I'm just finding the height first.
Yeah, I know, but
Then
on
we'll
the
use it.
calculator.
Oh, you have y1, let me double check, make sure I didn't do a typo. It's 1 over x minus 2 plus 1, yeah, that's right. So I called up the y1, that's in
Yeah.
variables, y variables, function. And then y1, and I did parentheses, -1.5.
-1.5, oh,
And then convert to fraction.
yeah, okay, that makes sense.
So that should give you 5 over 7.
Yep.
Plug in -0.5.
Oh, 3 cents.
There you go, 3/5. This does illustrate a bit of a danger. There's sort of a human temptation to say, the calculator told me so, therefore it must be right. May I humbly disagree. The calculator only does what you tell it to, and it's very stupid in that respect. You can do a whole bunch of brilliant stuff and have one little typo just because you happen to hit the wrong button. The calculator will not know it's wrong and it'll spit out the answer. What's the other midpoint, Michael?
My calculator died. I forgot
Well,
to charge
you can do
mine.
this by brain. What's the next midpoint I'm gonna plug in?
1/2.
1/2, correct. This teeny weeny little height at 1/2. So you're gonna plug in positive 0.5. And we got it? 1/3, good. The height here is 1/3. So the midpoint sum is going to be 5/7. 1 times 5/7 plus 1 times 3/5 plus 1 times 1/3. Feel free to type that into a calculator and then convert to fraction. So 5 over 7 plus 3 over 5 plus 1 over 3. Convert to fraction, and what you got? It's a little bigger than usual. Have we got it? 3 digit over 3 digit. Okay. Have we got it? What do you got?
173 over 105.
That's it. 173 over 105. And now, by the way, the reason I gave you fractions, because we're gonna have to use these answers in the last one, Simpson's rule. Tell me how. Let me see. Max, how do you use Simpson's rule?
Midpoint sum plus the midpoint sum plus trapezoid sum divided by 3.
Correct. So you're taking a 3-way average and counting the midpoint twice, because it's twice as heavy. This is one of the reasons why the fractions are important. Midpoint sum is 173 over 105. If you tried to type in the decimal, I have no idea how many spaces it is before the thing starts repeating, but it's way beyond the calculator. So if you tried to type in, oh, this is close enough, you're gonna get a wrong answer. So type in the exact answer whenever you can. So 173 over 105 plus 173 over 105, you can times 2 if you want. Plus 37 over 24. Close parentheses, divide by 3, and give me a fraction. It's 4 digits over 4 digits.
4,063 over
Got it?
2,520.
4,063 over 2,520. Now, last little favor to me. Give me decimals approximations for these. What is 23 over 12? Just give me 4 decimal places. Okay. Just type it in, yeah.
1.916, and then would you round up for the last one, so 6, 7?
Correct. To 4 decimal places, just round if you need to. 7 over 6, what's that?
1.167.
Yeah, 1.1667. So we've got, this is the upper sum, this is the lower sum. What's 37 over 24? Erase you.
1.5417.
Yeah, 1.5417. What's 173 over 105?
1.6476.
Yeah, 1.6476. And finally, 4063 over 2520. Go for it. 1.6123. If you had to make a bet, which one would you think would be most accurate? The last one. Simpson's rule is almost always more accurate than the other ones. Tell me how you get the exact area under the curve. Go. Michael.
Wait, the plug-in into the integral, whatever.
In the integral, tell me how. I've got my calculator ready. Tell me what to hit. You'll need to know how to do this too. Look at somebody else's. What do you type? Anybody? How do you get an integral? Math 9. Then what? What do you enter in first? Especially for people with old calculators. What do you plug in first? I mean, if you have the display, you can kind of go wherever you want. Yeah. If you have the display calculator, do the boundaries. From what to what, in this case?
-2 to 1.
From -2 to 1. What's the formula you type in? Yeah, 1 over x minus 2 plus 1 in parentheses. By the way, if you have an old calculator and you happened to put the y1 in the y equals screen, you can call up y1 in your integral and save time. It's totally up to you. I'm going to do that. Variables, y variables, function y1. Comma, what variable are you using? X. So for people with the display calculators, go to the D blank and put an X in the blank. And then comma, and then the people without the display calculators should go -2, 1. Give me your final answer. It does not convert to fraction, by the way. So what's the quote-unquote exact answer? It's not going to be exact, but give me 4 decimal places.
1.6137.
1.6137. Which one was closest? Simpson's rule. The midpoint sum was pretty good. Trapezoid sum, and these got further and further away. Make sense? The rest of the hour is yours to pound away at that. Doing the fraction ones with the variable on the bottom is a relatively challenging one, because when you do the antiderivative, you're going to get a logarithm. That's why we had the horrible answer that couldn't convert to fraction. Logarithms are irrational, usually. So, yeah. If you try and convert your final answer to a fraction and it doesn't convert, that's not your fault. But give me how many decimal places? 4. 4. Okay. Call me if we get stuck. Otherwise, I'll assume that is due tomorrow. For those of you who are still in the great beyond because of illness or travel, God bless you all. We'll talk to you later. Bye-bye.
Bye,
Yeah.
guys.